All right, I want to continue here with minerals, and we're going to break minerals up into several groups. And the first group on here are the carbonates, and carbonates include calcite and dolomite. And what's important about especially calcite, these two minerals, is that they're going to go into the rock called limestone. So limestones are important in that they're carbonates, right? And so they're marine rocks often associated with fossils, right? And one thing about what all carbonates share, they're going to have a base molecule, which is CO3. And it's a polyatomic molecule, which has a -2 charge. So if we combine that with calcium, for example, which is a 2+ charge, right, we get calcium carbonate, and calcium carbonate is the mineral calcite. So remember, the dolomite has some magnesium in it, so it'd be a calcium magnesium carbonate. Now for halides, these are often the evaporites, although the other evaporite mineral we see is gypsum, and so gypsum would be a sulfate down here. Yeah, so anhydrite gypsums. These guys are also evaporites, but the gypsum, which is plaster of Paris, is really a calcium sulfate. So this is a SO4, and it's going to have some number, N is sort of a placeholder of water molecules in it. So that's gypsum. So anhydrite would be the same thing as gypsum, except there's no water, right? So that's what they call it, anhydrite, without the water molecule. But they're both calcium sulfate. Now going back to the halides, right? So again, evaporite. So we're going to see the sodium chloride, which is halite, common table salt, and then the calcium fluoride here for the fluorite right here. So both of those are halides. Native elements: gold, silver. Well, diamond is only carbon, and so it's graphite, right? We talked about graphite already. Phosphates, so apatite, one of the more important ones we see. It's a calcium phosphate. It's a PO4, right? So that's our phosphate. And remember, phosphates are important as fertilizers. So oxides, so you can think of this almost like a rust, and so we're going to see the hematite and the magnetite. So for hematite, we're looking at Fe2O3. Silicates. So the key thing about silicates, these are our rock-forming minerals. And in a moment here, we'll talk about how we're going to classify these. So most rocks that you pick up are going to have silicate minerals. Remember, their base formula is another polyatomic ion, which is SiO4. -4. So that's a polyatomic ion. And then that's going to combine with metals like calcium, magnesium, iron, and it's going to give us a variety of different silicate minerals, right? Like potassium feldspar, olivine, quartz. You've probably heard of minerals like muscovite mica. There's two types of mica. There's muscovite and biotite. There's also pyroxene is another that's an important one. I wanted to name my first child pyroxene, but my wife said no. But pyroxene is a silicate. It's a single chain silicate. And then down at the bottom here, we got sulfides like galena. So galena would be, it's actually a lead sulfide, right? Lead sulfide. Obviously, these silicates, rock forming, and if we think about one of the first rocks, these are kind of primarily going to be in the igneous rocks, right? Those rocks that solidify, crystallize from a magma, right? And then there's erosion and weathering, and they're going to make other minerals. For example, the carbonates are primarily from a sedimentary rock, right? So we had sedimentary over here. So we're starting to think about rocks. So sedimentary rocks for the carbonates, the evaporites, those are all examples of sedimentary type deposits, right? We're going to break minerals into, especially these silicate minerals, these rock-forming minerals, into two broad categories: mafic minerals versus felsic minerals. The mafic minerals, the key thing about these mafic minerals sometimes they're called ferromagnesium, they're going to be rich in iron plus magnesium. Iron and magnesium. So think of this F for iron and the M for magnesium. And usually they're going to be in rocks like basalt lava, lava that erupts from the Hawaiian volcanoes, from the sea floor. Another rock, it's important, it's called gabbro. So gabbro is an igneous rock that cools and solidifies at depth, so it has large crystals. And then the minerals that are said to be mafic include olivine. That's a mafic mineral. I mentioned that pyroxene. The pyroxenes are really a group of minerals with a certain structure. They call it a single chain structure. But the one that's common in igneous rocks is augite. So sometimes you may hear the word augite pyroxene. And the other one that we know that occurs, especially in rocks from the mantle, is bronzite. Then the other mafic mineral we talk about is hornblende. Hornblende is very common in granitic rocks, intermediate rocks like diorites, not so much in basalt and gabbro. So when we start seeing hornblende, we're starting to change a little bit. And in fact, let's do the other one. It's Biotite Mica. So Biotite Mica is the black mica. In fact, there's a picture of Biotite Mica right over here. So here's the Biotite Mica. There's the augite pyroxene and the hornblende. And there's the olivine here. So let's talk about these two. So there's another group of rocks that are not really considered felsic, but they're not quite mafic. So they're somewhere in the middle. And hornblende and biotite are key components to those rocks. And these are the intermediate rocks. And those rocks, you've probably heard of them, the volcanic rock is called andesite. And the plutonic, or the rock that cools slowly at depths, very similar to granite, that rock is called diorite. So there's some of our mafic minerals, right? So now let's look at the felsic minerals. So when we see the word felsic, I want you to focus on this Si right here for silica. And when we see the word silica, we're really referring to SiO2, which is the mineral quartz. That's the formula for quartz. So the more quartz or silica in the rock, the more felsic it is, right? And so felsic minerals and rocks usually are of lower temperature, whereas the mafic ones are higher temperature. And examples of felsic minerals, we can have that mineral quartz. Then we also have the potassium feldspar. Usually we call it K-spar. But K-spar, the real variety of this one is called orthoclase. So orthoclase is a potassium feldspar. And when you see orthoclase and quartz in the rock, well, here, the typical rocks we see granite. So a true granite will have a high percentage of quartz and feldspar. And if you look at the volcanic rock, the equivalent to granite, but of magma that erupted, that has the same felsic composition, we call that rhyolites. So the volcanic rock rhyolite and the plutonic rock granite are going to have high concentrations of quartz and feldspar. But you can see there's some other minerals. There's some muscovite mica, some plagioclase in here. So let's look at the plagioclase. So plagioclase is sort of an unusual mineral. It's classified over here with a felsic, but plagioclase has sort of a range of composition. It can go from sodium rich, so Na is for sodium, so it can have a higher concentration of sodium. And sodium is one of those elements that prefers to be in the crust of the earth, so not in the mantle. But then it can range down to calcium. So basically there's a substitution between calcium and sodium in the crystal structure. And so calcium is not, it can go in the crust less mafic. I don't want to say it's from the mantle, but there is some calcium in the mantle, but quite a bit in the crust. But it's going to be less mafic. Plateau Clays is usually in the intermediate rocks, right? So that's going to be in those andesites and the diorite. So really the only felsic rocks, so those are the intermediate rocks. So really the only felsic rocks are these granites and rhyolites, right? So just by looking at the felsic versus mafic minerals, we can separate them into different groups. Muscovite mica is the clear or white mica, but when we see them in granitic rocks, it suggests that these granites, sometimes we call these S-type, and S-type refers to that their origin was probably from melting pre-existing rocks, right? So we're going to have maybe like a continental crust origin. So these may have been pre-existing continental rocks that were melted and then made into these. So they have old chemical signatures and not really coming from the mantle. Granites that come from the mantle, sometimes we call those I-type granites, but let's not worry about that right now. But I just want to point out is muscovite, when you see that, it's a good indication that these granites are quite evolved. They maybe a magma from the mantle comes up and then melts the surrounding country rock, the adjacent rock, and that produces a new magma which makes these S-type granites. So now I want to talk here about the rock cycle. And the key thing about the rock cycle, it's going to show the relationship between the different rock types, igneous, metamorphic, and sedimentary. So we need to start off, when we talked about Earth, the first couple 100 million years of Earth may have had these magma oceans, and it was probably a magma planet until it cooled enough so that we can form rocks. But the key thing is the rocks begin to cool, right? And in that process, depending on the rate of cooling, they're going to form minerals. So the other word we use is crystallize. Eventually you're going to form igneous rocks. One question I have in the study guide is, all igneous rock share one common characteristic, is that they cool, solidify, crystallize from a magma, whether that igneous rock is a volcanic rock or a plutonic rock. So igneous rocks come in two varieties. One that cools fast because it erupted from a volcano, so cooled on Earth's surface, small minerals, fine grain, and one that cooled very slowly, Pluto. Remember, Pluto is a Roman god of the underworld. And so this would be like our granite, coarse grain, big crystals in it. Volcanic rocks, like basalt, fine grain, small crystals. So all igneous rocks cool from a magma. And you can see that magmas range from anywhere of around 1200 degrees centigrade to about 600. And remember, these would be the mafic magmas, the hotter magmas. And up here, these would be the felsic, the cooler ones. The ones with quartz and potassium feldspar, the orthoclase. So at some point, we're going to see weathering. And that's one of the key things that's going to happen here. We're going to see weathering. And I want you to think of weathering, and we'll talk quite a bit about this in this class especially. Think of it as a liberation of components. You're releasing either minerals or chemical elements, ions, from the source rock, right? And then, so that's a liberation of components. But now you got to move them. So we're going to move them through a process called erosion. So think of erosion as a transportation, but weathering as a liberation. So that's a liberation and transport. You'll see that there's physical weathering and chemical weathering. We'll get all into the different types of weathering. But then we're going to move that stuff. So we think about some agents of transportation. So what agents could move the weathered material? Well, rivers, wind, glaciers, gravity, downslope movement of materials. But what we get out of here, think about when you go to the beach, we get loose material, which is sediment. It's not a rock yet. It's just loose material, and we call that sediment. And the sediment can come in a variety of different sizes, from boulders, cobbles, pebbles, granules, sand, or mud-sized sediment. And so the key thing about this is loose. It's not a rock yet. It's not a rock.